Hello everyone. Today in this video we are going to do the Unit 8 exam review, and specifically I'm going to start off with the multiple choice. So 14 questions. The time frame for that is 21 minutes to or 1.5 minutes per question. Let's go ahead and get started, shall we? Alright. That looks like it's working. I have my bad pen today, so if it stops working, I'm just going to hit it on the desk because hitting it usually works. So if you hear loud bangs, that's why. A solution is prepared by adding 100 milliliters of 1 molar acetic acid, that's HC2H3O2, to 100 milliliters of sodium acetate. The solution is stirred and the pH is measured to be 4.37 or 7.3 rather. After 3 drops of HCl are added to the solution, the pH of the solution is measured and is still 4.73. Which of the following equations represents the chemical reaction that accounts for the fact that the acid was added but there are no detectable changes in pH? All right, so we're creating a buffer. We have acetic acid, a weak acid, and we have acetate, its conjugate base, which means we have a buffer solution. We are creating a buffer solution for ourselves, and the buffer solution is doing what buffer solutions do, and that's resist changes in pH when we add acid or base to it. The way we figure out the reaction that's happening is we write the major species. So we have acetic acid, we have the acetate ion, we have sodium that comes from the acetate ion because that's in a soluble salt. And then we have water, we always have water, and the last thing we have is when we add hydrochloric acid, we are adding H plus and Cl minus. The strongest acid is the H plus, the strongest base is the Ac minus, so the reaction that happens is H plus Ac minus yields acetic acid. Or we can say H3O plus acetate yields HAC plus H2O. This is the more accurate reaction to what's happening, which is D. D is the correct answer. Essentially, in simpler terms, a buffer is made out of an acid and its conjugate base. If we add acid, the conjugate base steps up to the plate and reacts that acid away. If we add base, the acid, the weak acid, steps up to the plate and reacts that base away. And that's how buffers mitigate changes in pH. A 40 milliliter sample of the weak base C5H11N was titrated with 1 molar hydrochloric acid. Based on the resulting titration curve shown above, which of the following provides the best estimate for pKb and Kb of the weak base? So we're trying to find pKb and Kb, and we're given a titration curve. The point that's going to help us here is the halfway point. So let's find the halfway point. The equivalence point is at 40, which means the halfway point is going to be at 20, so right there. And that pH looks to be at 11. At the halfway point, pH is equal to pKa. It does not matter that this is a weak base strong acid titration. pH is equal to pKa. That is the relation, which means the pKa is equal to 11. The pKb is going to be, therefore, 14 minus 11 because pKa plus pKb is equal to 14. So the pKb is going to be around 3, which is what A says. On the basis of the information above, what is the approximate percent ionization for nitrous acid, which is a weak acid, and 1 molar in a 1 molar nitrous acid solution? So we're trying to find the percent ionization. Percent ionization is basically how much does the acid dissociate? How much does it ionize? Or I should use ionize. How much does the acid ionize? So in other words, what we're looking for is how much H plus do we get over what concentration of HNO2 starts at the beginning. So what we're going to do is let's create a rice table for ourselves. The reaction that we're going to use here is the ionization of nitrous acid with water. So we have HNO3 plus NO2 yields H3O plus NO2, or NO, this is a mistake, it should be NO2 minus. The reason that I didn't just use this reaction is because this puts it in terms of H plus, which isn't the most accurate as to what's happening, because remember H plus is really H3O plus, so this is the accurate representation of the reaction. And the reason I did that is just to show that this is a Womix table. This is this version of a Rice table. So we're plugging in concentrations here. The concentration of HNO2 at the start is 1. We have 0 of these. We're going to go minus x, 1 minus x, and x when we add the I and the C together. The Ka expression is the concentration of H3O plus times the concentration of NO2 minus over the concentration of HNO2. So plugging in the expression and plugging in the Ka that we have, we get 4.5 times 10 to the negative fourth equals x squared over 1 minus x. Now we need to find x. The reason that we're solving for x is because x is what's going to give us how much H3O plus we have. And H3O plus, that's going to let us find out what the percent ionization is. A couple different ways we can find x. I'm going to assume that this is a weak acid, which it is. It has a very low Ka, which it does, which means that the final concentration of HNO2 is really just this initial concentration of HNO2. It's going to have a negligible change, which means this denominator goes to 1. And then I can just say x squared is equal to 4.5 times 10 to the negative fourth. So the square root of 4.5 times 10 to the negative fourth is equal to 0.021. That is the concentration of H plus that we have. To find the percent ionization is going to be equal to that concentration divided by the initial concentration, which is 1 times 100. So the percent ionization is going to be equal to 2.1%, which is D. The pH of a solution is prepared by the addition of 10 milliliters of 0.002 molar potassium hydroxide to 10 milliliters of distilled water is closest to. Potassium hydroxide is a strong base. What that means is we can get the pOH by taking the negative log of the concentration of the KOH. Now, we can't just plug into this concentration yet because we are adding 10 milliliters of distilled water, which means we're diluting it. We're diluting it first. So before we plug in a concentration, we have to find out what the new concentration after dilution is. And to that, we go to M1V1 equals M2V2, our trusty dilution equation. The initial molarity is 0.002. The initial volume is 10 milliliters. The final molarity is what we're solving for, and the final volume is 20 milliliters. Once we add that extra 10, we get to 20 milliliters in total. The dilution equation doesn't need it to be in terms of liters. You can use milliliters as long as milliliters on both sides. So 0.002 times 10 divided by 20 is 0.001 molar KOH, which makes sense. If we double the volume, we have the concentration. So this is when I'm going to plug into here. So pOH is the negative log of 0.001, negative log of 0.001 is 3. So the pOH is equal to 3, which means the pH is 14 minus that, which is going to be 11. For 5, on the basis of the information above, a buffer with a pH of 9 can be best made using... Okay, so we're trying to create a buffer with around a pH of 9. If we look at the Hendy-Haas equation, pH is going to be equal to pKa plus the log of the conjugate base, or the base thing, over the weak acid, over the acid thing. So specifically focusing on this section. pH in a buffer solution is largely dictated by pKa. So we should be finding which of these Ka's, when we take the negative log of, because pKa is just the negative log of Ka, is closest to 9. And the answer I can just see by looking at this exponent is the H2PO4. But just for fun, let's go and plug them in. So if we do negative log of 7 times 10 to the negative third, we get a pKa of 2.15. If we do negative log of 8 times 10 to the negative 8, we get 7.09, and if we take the negative log of 5 times 10 to the negative 13th, we get 12.30. The weak acid, whose pKa is closest to 9, because that's where the pH will more or less end up, is this acid. So this should be the weak acid, and the conjugate base should be this minus an H+, because a conjugate base is what is left after the acid once the acid has donated a proton. So it should be H2PO4 and then HPO4 2-. The answer is D. Now the way to get this buffer to a pH of around 9 is to use these two, but then add more of this guy than we have of this guy, because then that would make this ratio greater than 1, which means we'd be adding onto that pH. Also, last thing, just looking at these questions, A does not create a buffer solution. C does not create a buffer solution because that is not a weak acid in its conjugate base. The only ones that create a buffer solution are B, D, and E, so you shouldn't be picking A or C anyway. Weak acid and its conjugate base is what a buffer solution is. All right, let's keep going. The net ionic equation for the reaction that occurs during the titration of nitrous acid with sodium hydroxide. Nitrous acid is HNO2, sodium hydroxide is NaOH. This is a weak acid and this is a strong base. Now, even if you didn't know that, if you're not very good with naming, you can probably figure that out via context clues. This thing is nitrous acid. It's the thing that's in all of them, other than this one. All right, the way we get reactions, net ionic equations, in acid-base reactions is by listing the major species and picking the best acid and the best base. So what do we have in this system? We have water. We always have water. These are always aqueous solutions. We have HNO2, which is a weak acid, which means we don't break it up. And then we have Na+ and hydroxide, OH- coming from the strong base, because sodium hydroxide is a strong base. The best base is OH-. The best acid is the nitrous acid, so the reaction is going to be the nitrous acid combining with the hydroxide, which looks like E is the thing that does that. A 20 milliliter sample of 0.125 molar monoprotic acid solution is titrated with sodium hydroxide of unknown concentration. Based on the titration curve above, what is the molar concentration of the sodium hydroxide solution? The way we're going to find the concentration of the sodium hydroxide solution is by looking at the equivalence point. This has nothing to do with pH, this question. This question has to do with how many moles of sodium hydroxide was needed to get to equivalence point. Because at the equivalence point, the moles of the acid equals the moles of the base. So let's find out how many moles of acid we have. We have 20 milliliters of 0.125 molar. So if we do 20 times 0.125, we get 2.5 millimoles. Okay, so we have it took 10 milliliters of NaOH to reach equivalence point. What concentration does that base need to be so that we have 2.5 millimoles of base? Because that wouldn't be when moles of acid is moles of base. And the answer is when that concentration is doubled, 0.250, which is C. So if we do 2.5 divided by 10, we get 2.250. You can also solve this question by doing M1V1 equals M2V2, where M1 is 0.125, V1 is 20, M2 is what you're solving for, and your V2 is 10. X needs to be 0.25. Which of the following species is the strongest base in the reaction represented above? Okay, so picking the strongest base, just looking at a reaction, strong things do not form. Strong things ionize, strong things dissociate, reactions go away from strong things. So whichever base is stronger is going to be the one that the reaction is moving away from. And we can see that based off the K. This K is very small. Remember from Unit 7, K is really just a measurement of product concentration over reactant concentration. So if K is really small, that means at equilibrium we end up with way more reactants than products, which means our reaction is actually going this way. The reverse reaction is favored. The stronger base, therefore, because in an acid-base reaction, there's two bases and two acids. There's an acid and a base on the left side. There's an acid and a base on the right side. The two bases we're picking between are this guy and this guy. These guys are acids. Don't pick those. So it's not B and it's not C. It has to be A or D. The one that's stronger is going to be the one that's dictating which way the reaction's going. And the reaction's going from products to reactants, so that means D is the stronger of the two bases there. For questions 9 and 10, use the titration curve below. So we're using this titration curve. We have 100 milliliters of 0.025 molar acetic acid is titrated with 0.100 molar sodium hydroxide. Which of the following indicators is the best choice for this titration? All right, we want an indicator that is going to be in the range of when the equivalence point is. So where does the big jump occur? The big jump, it looks like it's happening from like 7 to 11. So we want to be in that range, probably even more, probably closer from 8 to 10. We want to be right from 8 to 10. That's the vertical portion of the graph. That's when we want our indicator to change during the equivalence point. So which one is from 8 to 10? D is the best option. C can be another good option. It's the second best option. However, it's not. D is more within that range. C is going to start to change a little bit before equivalence point. It's going to start to change right around where W is. So D is the answer, the phenolphthalein. Which part of the curve corresponds to the optimum buffer? The optimum buffer in titration occurs at the halfway point. At the halfway point, that's where pH is equal to pKa. That's when we're in the middle of the buffer zone. That's when the buffer is at its most effective, when we have equal concentrations of acid and conjugate base. You can do a Rice table to see that, but we're looking for the halfway point. If the equivalence point is at 25, the halfway point is at 12.5, so V is the answer there. So point V is when the optimum buffer occurs. All right, 11, a student was given samples of 4 different unknown liquids. The unknown liquids are, naming. Say these names. Propylamine, pentane, 2-propanol, and propanoic acid. The structures and molar masses of the compounds are shown in the table above. On the basis of this information, the student designed some experiments to identify the samples. Of the following, which identifies the aqueous solution of the compound that will have the highest pH? The highest pH is going to be the compound that's the best base, or the strongest base. So essentially, basically, what we're doing is we're looking at which of these compounds is going to be the best at accepting a proton, because that's what a base is. A base is something that accepts an H+. So looking at these structures, which of these looks like it can accept an H the best? And to me, it just looks like propylamine. The first one here has a nice spot to put that H. It's definitely not pentane. Pentane's at capacity. Propanol also looks like it doesn't really have some place to go, although I guess it technically can go on that oxygen. Propanoic acid, other than the name of it being an acid, to sway you against that, it looks like it does have a place it can put an H, but not as neat as propylamine. So we're looking for propylamine. So A says propylamine because the lone pair of electrons on N can accept H plus from the solution, and that's the correct answer. If we look at the rest of these answers, they're also going to say stuff that are contradictory, so we can do some process of elimination. B says pentane because it produces the largest number of H plus ions. That is not what makes something have a high pH. That's what makes something have a low pH. That's an acidic thing. 2-propanol because it completely dissociates into C3H7 plus and OH minus. No, it can't do that because that would mean it's a strong base. Strong bases completely dissociate into OH minus, and that's not one of the strong bases. D says propanoic acid because it dissociates into H plus and C3H5O2 minus. That also is something that's creating an acidic solution. A is the only thing that makes sense. A is the only thing that matches up with what a base does, and 2 doesn't lie to you. Which of the following statements about the pH of 0.010 molar perchloric acid is correct? Perchloric acid is a strong acid. The way we get pHs of strong acids is we just take the negative log of the concentration, because the concentration of perchloric acid equals the concentration of hydronium, because strong things dissociate, they ionize completely. So if we do the negative log of 0.01, negative log of 0.01, I'm fumbling on the calculator today, negative log of 0.01, also my calculator is about to die, is 2. So we know the pH is equal to 2. The pH is equal to 2. And the reason the pH is equal to 2 because this is true, so the concentration of H plus is just the concentration of the strong acid, which is A. This does not make mathematical sense. If you do 2 times 10 to the negative second, you won't get a pH of 2. You get a pH of under 2 if you plug that into your calculator. Just for fun, negative log of 0.02 is equal to 1.7. Each particle diagram shown is a representation of an aqueous solution of one of the acids listed in the table. The molarity of the acids in the solution are the same based on the information which particle diagram best corresponds to the indicated acid. All right, so we have to match up these 3 acids, 1, 2, and 3, with these 3 solutions. We're given that each one is the same molarity. The difference is these acids, which are all weak acids, by the way, are going to dissociate, are going to ionize into a different amount of H3O+. So basically, we're just asked to rank the strength. This one is going to be the strongest. This one is going to be the weakest. So we have a list of 3 oxyacids. How do we determine the strength of oxyacids just by looking at the molecule? The answer is the more electronegative this element is, the stronger the acid will be. So HClO3 will be the strongest acid. So let me redo these. Let's call this A, B, and C. So that means A is going, or I don't even need to do that. This one's going to be HClO. Next comes HBRO. This one's going to be HBRO. And the weakest one is going to be HIO. For this, I also like to do what I call the perchloric acid test. Listen, it can be hard to remember the rules for comparing strengths of oxyacids. However, so what I like to do is always just like to think about perchloric acid. I know that perchloric acid is a strong acid. That is one of the 6 strong acids. I also know that HBrO4 and HiO4 are not strong acids. This guy's strong, these two are not. So what that tells me is there's something about chlorine that's making it stronger than bromine or iodine in oxyacids. Chlorine makes something stronger if it's in an oxyacid, because HClO4 is a strong acid, whereas these other two are not. So just looking at the answers, which of these corresponds to the right thing? Diagram 1 corresponds to HClO. Nope. Diagram 2 corresponds to HClO. Nope. Diagram 2 corresponds to HIO. That is the correct answer. Diagram 3 corresponds to HBrO, and the answer is also no there. Also, I don't think I said this, but the stronger the thing is, the more it dissociates into H3O+. So the reason why I know this guy's the strongest is because it has the most H3O+. All right, last question. The value of Kw at 37 degrees is 24 times 10 to the negative 14th. Which of the following statements about the pH and pOH of pure water at 37 degrees is correct? When we change the temperature of water, the entire pH scale changes. Kw being 1 times 10 to the negative 14th is only true at 25 degrees Celsius. And this number is what dictates our pH scale, because that's the number where H plus times OH minus equals, is the Kw. Now if H plus and OH minus do not equal 1 times 10 to the negative 14th, if they equal instead 2.4 times 10 to the negative 14th, then what becomes of pH and pOH? Well, let's just do the math real quick. When it's neutral, when it's pure water, then these two are equal to each other. So we can just say that they're both x, and we can say x squared is equal to 2.4 times 10 to the negative 14th. To find x, we can take the square root of that number, 2.4 times 10 to the negative 14th. And we get x is equal to 1.55 times 10 to the negative 7th. And if we take the negative log of that number, that negative log gives us both of the pH and the pOH. They're still going to be equal because x was both H plus and OH minus. So negative log of that number. And we get a pH of 6.81. So the pH and the pOH, they're both the same number since this is a perfectly neutral solution. That's when pH and pOH are the same. And they're going to be less than 7. So pH is equal to pOH, but it's less than 7 because the dissociation is greater to a greater extent at 37 than 25 degrees Celsius. Just conceptually, if we look at the self-ionization of water, 2H2O yields H3O plus OH minus. A bigger K, because K is going up when we increase the temperature, means this reaction progresses more this way. It moves more to the right. That's what Ks tell us. If K is bigger, we progress more towards the product. The products are favored more, which means the concentration of both of these things are going up. The pH is a measurement of how much H3O plus we have. The pOH is a measurement of how much OH minus we have. The bigger those numbers, the smaller the pH is, or the smaller the pOH is. The more H3O plus, the smaller the pH goes, right? Because more acidic means more of this, and more of that means lower pH. So both pOH and pH are going down. All right, well, that is it for the multiple choice questions. As usual, if you have any questions, ask me in class. Otherwise, I will probably do the FRQ another time, but I'll get this one uploaded within 48 hours. All right, that is it. I will sign off. See you guys. Oops.